SuperEarth breaking news.
Good morning. There are leading-edge discoveries in super-Earths and their atmospheres. I am Merel.
And I am Aniek, and we're breaking down the top discoveries for super-Earths and their atmospheres.
But first, the facts. Super-Earths are rocky exoplanets that have a mass between 1 and 10 Earth masses. And a more strict definition adds a radius limit between 1 and 2 Earth radii.
The first super-Earths were detected in 1992 by Woltzkan et al. These two super-Earths orbit a pulsar, which makes their discovery slightly more questionable and causing them to miss out on the Nobel Prize. The first super-Earth around a main sequence star was observed in 2005 by Rivera et al., and many super-Earths have been discovered since.
Major breakthroughs have been made in the knowledge of the contents of their atmospheres. These can determine if there is a possibility for life on a planet. To know more about this, we will go to our correspondent Casper. Hello Casper, how is the atmosphere?
Well, thank you, Merel. The atmosphere here is great, by the way. It's mostly nitrogen and oxygen, well, Earth-like. Well, super-Earths, they can obtain atmosphere like ours via two different degassing processes. Degassing during accretion and degassing from tectonic processes. These processes are caused by capture of different kinds of meteorites. On one hand, chondrite material, which is the most primitive meteorite class, containing a variety of silicate components. And on the other hand, acronites, which are believed to contain silicate remnants from planetesimals at iron cores and silicate mantles. Generally, acronites have lower water contents than chondrites. In the case of chondritic material, metallic iron reacts with water to oxidize the iron and form hydrogen as well. This process continues until either iron or water is exhausted. When water is exhausted, it will form a metallic core. If iron is exhausted, there will be no metallic core, and the atmosphere has water and hydrogen compounds. With achondritic material, the planet will have an existing core with a silicate mantle, and that mantle will have a form of a magma ocean that will solidify over time. The final planet will have a metallic core with water compounds in the atmosphere, and a silicate mantle has traces of volatiles. When additional water is added to the planet, the magma ocean will be enriched with water, and it will form an ocean of either liquid or supercritical water. All atmospheres that I discussed are predicted to have carbon compounds as well as helium and nitrogen traces. Based on a wide range of asteroids composition on Earth, the super-Earth's composition will be very diverse. In extreme cases, mass in the atmosphere could range from 1 to 20% of the planet's total mass. The abundance of the elements in the atmosphere depends on which type of asteroids have contributed to the formation of the atmosphere. Well, that's in 2017. Atmospheric features were found in super-Earth GJ1132b, which is a planet of 1.6 Earth masses and has a radius of 1.38 Earth radii. It was the smallest planet with signs of an atmosphere at the time, and south of it all, that based their results on observations of the planet in 7 different wavelengths. In the Z-band, which is around 900 nanometers, a large planet radius was found. At this wavelength, a prominent water absorption line is present, which indicates that the measured radius included an atmosphere containing water. When compared to theoretical models, the research group have predicted a water mixing ratio between 1 and 10% on the planet. Now, it should be noted that it might be possible that methane could have bumped up the radius in the Z-band instead of water. Therefore, the group advocates for more detailed observations to study the atmospheric features of the super-Earth. Now back to the studio.
Thank you, Casper. Our correspondent Gabriella will discuss the possible features of these components in the spectrum of the atmosphere. Now to Gabriella, all the way from planet GJ1214b.
Hi, thank you, Aniek. I'm Gabriella and I'm talking to you from the super-Earth JG1214b. The measurements from Earth and space are until now insensitive to measure the predicted features in the spectra of the atmospheres of super-Earths. This is due to the low resolution of the telescopes. There are some models made about spectra of super-Earth, and one is of this planet I'm on right now, JG1214b. In this model, Gandhi et al. Consider a metallicity of about 100 times the Earth's for the molecules water, methane, and NH3. They calculate the cross-section by considering a certain temperature-pressure grid and broaden the lines into a Vogt profile. Together with some other parameters like the resolution and wave number, they then find the cross-section for these molecules. And together with the number densities of these species, they then find the transit depth. And that's actually what we see right here. And as you can see, on the left, the features are clearly visible for a lot of the species, while on the right, we only see a few features which are more broadened. This broadening is due to the higher opacity at higher wavelengths. And this broadening also causes that we don't see other features which also could be in that range. So this is what we expect to find when we would look at this planet with higher resolution telescopes. But this would be for a cloud-free atmosphere. And when I look up, I can see that there is probably a high altitude cloud deck. And this will have influence on the measurements. For instance, the clouds can have an influence on the albedo spectra, which then will have influence on how we will see the features. So this influence, what the influence is not certain yet, but this will be interesting to find out when we can compare the high resolution data with this model. So the transit depth of this model was made by considering a certain temperature pressure grid. While for another SuperEarth, 55 CNCE, they actually also simulated this temperature pressure grid. They have done this in two stages. First, an analytical stage where they set up initial values, and a second stage, layer by layer, which is more objective but also takes a longer time. So they combine these two to get a fast but accurate temperature pressure grid of this exoplanet. And this is what we see here. And it actually looks a lot like the images shown by Jamila in our lectures. And we can see that at 10 to the power minus 2, the atmosphere heats up due to the absorption of light by the molecules. And at 10 to the power minus 1, this heating stops due to optical thickness of the atmosphere. So from here on, they could have gotten the emission spectra of this planet, but unfortunately in the paper they didn't do this for this SuperEarth. So we have seen how the temperature pressure grid can be simulated, and also what a spectra can look like for SuperEarth. And now back to the studio.
Thank you, Gabrielle. Now we know more about how the spectra of the atmosphere are simulated. We want to know how it behaves. Let's go to the weather with Merel.
Thank you, Mi. I cannot tell you if it is gonna rain, but I can tell you more about the winds based on the circulation models. But first a short note. These circulation models are based on SuperEarth GG1214b. So this weather forecast is only relevant for people who live at a SuperEarth like this planet. In the models, most of the time an equatorial superrotating jet and a pair of high latitude jets are present. Now, let's take a look at the effect of the global mean surface pressure and the albedo. At higher surface pressures, the temperature is higher, the speed of the equatorial superrotating jet decreases, and the speed of the high latitude jet increases. At higher albedo, the temperature and the speed of all the jets decreases. Note, this is only true for a gray atmosphere dominated by greenhouse gases. When you live at an H2 helium-dominated atmosphere, we can take a look at the metallicity. When the metallicity is increased, the speed of the equatorial superrotating jet is higher, and the speed of the high latitude jets are less strong. When you live lower in the atmosphere, you will not suffer so much from these winds. Do you live in an H2O dominated atmosphere? These winds are less strong and reach to higher pressures. In a CO2 dominated atmosphere, The high latitude jets dominate circulation and reach in the whole pressure range. The equatorial superrotating jet is very weak. In a model with both H2O and CO2, the circulation behaves like an intermediate between the previous two models. The equatorial superrotating jet is weak and the high latitude jets dominate circulation. And now, back to you, Aniek.
Thank you, Merel. We haven't considered that the atmospheres could also escape a planet. To tell us more about this, we will talk to our correspondent Aniek. Thank you, Aniek. The process of losing gas from the atmosphere is called atmospheric escape. Since hot Jupiters were abundant among the first observed exoplanets, atmospheric escape is initially characterized for these planets, and this process is less understood for super-Earths. However, there are things that we do know. The genes parameter indicates which escape mechanism dominates on a planet by comparing the gravitational energy with the thermal energy. Since super-Earths are relatively low-mass planets and generally are close to their host star, granting them a high temperature, hydrodynamic escape dominates. Hydrodynamic escape is explained by Parker in 1958 to be the only solution to get a hydrodynamic equilibrium when the planet does not experience an external pressure. Particles move outwards due to their high temperature, which causes a pressure gradient force that expands the atmosphere. In 2013, Lummer et al. Looked at 7 different super-Earths and found, using a 1D hydrodynamic upper atmosphere model, that 6 of these experience Rush-Lobe overflow. They have a mass loss rate of 10 to 100 times what is found for a typical hot Jupiter. Yet, the atmospheres of these super-Earths will not be affected by atmospheric escape in their lifetime. Although this method has not yet been successful for super-Earths, atmospheric escape is directly observed around hot Jupiters, and once the resolution of our telescopes improve, the same can be done for super-Earths. Atmospheric escape can be observed using the transit method and examining the radius that is found for the planet and its atmosphere. If this radius exceeds the Rush-Lobe, then there is atmospheric escape. One characteristic that is still uninvestigated is the influence of a magnetic field to the atmospheric escape. The outflow will be ionized and hence could be affected by a magnetic field. If this causes even a small correction to the mass loss rate, it could have a significant effect on the evolution of these super-Earths. And now back to you in the studio.
Thank you, Aniek. It is clear that although many discoveries have been made, there is still room for improvement. And what better way to see what these improvements could be than talk to our future correspondent Casper. Hello, Casper.
Thank you, Aniek and Merel from the past. I'm currently standing here in the year 2029, where we just witnessed the launch of Ariel. Ariel is the atmospheric remote sensing infrared exoplanets large survey mission. And with Ariel, we hope to survey around 1,000 hot exoplanets that are close to their host star to search for their composition. On some planets, Ariel will perform deep surveys on their cloud systems and study the atmospheric variations on scales from days to even seasonal changes. Then the James Webb Space Telescope, which is projected to launch in the next couple of years, will use the transit method to observe exoplanets in the infrared band to search for their atmospheric features. This is because the infrared band has the largest number of spectral features for molecules in the atmosphere. The transit method of these 2 highly accurate space telescopes will provide us with crucial knowledge on the atmospheric features of super-Earths. I'm going to say the next few years will be super exciting. And now back to the year 2020.
Thank you, Casper. So the highlights of tonight. Degassing is the main process of formation of atmospheres on super-Earths, and their mass could reach up to 20% of the planet's mass in extreme cases.
The features in modeled spectra of molecules in the atmosphere are dependent predominantly on the metallicity, temperature, and pressure of super-Earths.
In circulation models of super-Earths, an equatorial superrotating jet and high latitude jets are present and depends on many different parameters.
Atmospheric escape for super-Earths is dominated by hydrodynamic escape and Rush-Lobe overflow.
Dit was SuperEarth News with our correspondents Casper and Gabriella. I am Merel.
And I am Aniek. Good night.